Okay, so this is my first attempt for standard 2.2. I decided to do problem 2.10. The problem asks for the state spin up in the y direction. Calculate the expectation values and uncertainties for measurements of Sx, Sy, and Sz. It also asks us to draw a diagram of the vector model applied to this state and reconcile your quantum mechanical calculations with the classical results. So the first step is to find the expectation values for Sx, Sy, and Sc in this state. We can calculate these using this formula right here. Here A is an operator and phi is in the prepared state. Using this formula we can get our expectation values. The expectation value for Sz is going to be this, where we simply just plug in. We can rewrite this in matrix notation as shown right here. And yes, we get 0 h bar. For Sx we use the same process. We go through and find that Sx equals 0 h bar as well. And for Sy we do the same thing and we get h bar over 2. Now that we have our expectation values, we can calculate the uncertainties for the measurements. The standard deviation, delta A, represents uncertainty in the results of an experiment. We know that changing the experiment will not affect the uncertainty because uncertainty is inherent in quantum mechanics. To do this, we can calculate the minimum uncertainty allowed, and doing this we use the Heisenberg uncertainty principles. First we will calculate the mean square of the operators starting with Sz. Here we use this method right here as shown. Again, we can solve this in matrix notation and we get h bar squared over 4. Knowing that the mean operator in Sc is 0 h bar, using our equation for standard deviation, we see that the standard deviation Sc is h bar over 2. Again, we go through the same process for Sx. Here we get again a standard deviation of h bar over 2, and lastly we do the same process for Sy and we get a standard deviation of 3 over 4 h bar squared. This implies that the length of the spin vector is square root of 3 over 2 h bar. And lastly, here is my vector model to reconcile the quantum mechanical calculations and the classical results.